what you might have noticed with some of our integrals, probably in the trig integrals it happens the most, when we have those powers, and if you're doing integration by parts or something, you end up getting another trig integral, but the power's a bit lower. And then you've got to apply the technique again. And so sometimes what we do is we just come up with a formula on, hey, how can we just reduce these powers without having to integrate until we get to a nice low power, which is easy. So that's the idea of creating a reduction formula. Okay. Sometimes known as recurrence, you might see that word rather than reduction. You might see it called a recurrence formula. But as I say, it usually involves raised to a power. So integration by parts is by far the most common way of doing it. That doesn't mean it always has to be, and we'll look at an example where we don't use it. But first of all, let's look at one where we do use integration by parts. So 1 on e x log x cubed. Now it hasn't actually said to create a reduction formula here, you'll notice. So if I wanted to create the formula, then instead of having power of 3, I'll just replace the power with n and call this integral n and create the formula. So where to go? This brings up another difference with some questions. Some questions, they'll tell you what the formula is, which is nice, because that way in an exam situation, if you can't get that formula, at least you've got it there and you can show you know how to apply it and use the formula. When you get questions like this, if you want to use a formula, obviously they haven't given it to me, so I'm going to have to work out what it is. So I'm going to do it by parts. I'm going to actually choose to be the log x to the power of n. And I suppose that makes sense, because remember dv we choose so that it can be integrated. And we don't know how to integrate log to the power of n. So my du, bring down the power, lower the power, diff the inside. dv becomes x, so v is a half x squared. Alright. So it's a definite integral. It's from 1 to e. Now if I substitute e into this, I'm going to get log e, which is 1. 1 to the power of anything is going to be 1. So it doesn't matter that if I know n or not for that. And so e squared, well half e squared, we'll end up with minus log of 1. And log of 1 is always 0. So actually I can work out that part of the definite integral. And if I look at the second part, what have I got? I've got x log x. It's basically the same integral, but the power has been reduced by 1. So what I now have is e squared on 2 minus n on 2, but this integral I could call I n minus 1. And so there's a formula now that allows me to reduce it by 1, and I don't have to keep using parts over and over again. So I now know that this would be I3. So I3, using the formula, will be e squared on 2 minus 3 on 2 lots of I2. I2, e squared on 2 minus I1. Tidying that up, I now have minus e squared on 4 plus 3 on 2 I1. Well, I'm going to use it again, because even integrating log to the power of 1 is a bit tricky. I would have to use parts, so let's reduce it again. And I1 would be e squared on 2 minus a half I naught. That's better, because to the power of naught would make that equal to 1, and I've no longer got a log function. And so I naught, I'll go and actually work that out, and that is integral of x, a nice easy integral to do. Add 1 to the power over power. We get a half of x squared, so that's 3/8 of x squared for our one. We can sub in and get the answer. So it's 4 questions where you use integration by parts a lot of the time, but it's saving us using integration by parts over and over and over again, because we've generalised that process, and then we just use the formula and can come up with an answer. Now another way people like to use integration by parts, I guess it's just a personal preference, is like this, is they'll actually start with I naught and work out what I naught is. So they sort of say to themselves, if I was to keep reducing this, what would be the last one I'd have? And you'd stop at naught, because to have log x to the power of -1, well, that's not going to really help us. So they know I naught is where we stop, and actually work out what I naught is first, and then build it back up to I3. They say, well look, I1 then would be e squared on 2 minus a half I naught, sub in what we just worked out for I naught. I2, sub in what we then have worked out for I1, and then they go, okay, well now I can work out I3 and get the answer. It's just a personal preference, I guess, which way you go. Whether you start at the 3, work your way down to naught, or you start at the naught and build it up to 3. Integration by parts is the commonest way of getting reduction formula, but as I say, it's not the only method. If I've got something like this, cot to the power of n, if you remember when we did tan to the power of any power, we used the same technique every single time, and it did not involve integration by parts. So I'm just going to use that particular technique. Cot to the power of n, well, if you remember what we did for tan to the power of n, we factorised that, we split it into, we took the squared out. I can change cot squared to cosec squared minus 1. I end up with cot to the n minus 2 cosec squared. I can do that using a simple substitution. And then the second one, well, it's my integral, but I've reduced the power by 2. So if I let u equal cot x, du will be minus cosec squared. So my first integral is minus u to the power of n minus 2. And the second integral, as I say, is just I n minus 2. Add 1 to the power over the power, sub back in for u, and I've now got a formula for I n. Yeah, because we're using trig identities a lot of the time, you'll see those powers will go down by 2 a lot of the time. So if we know we don't have to use parts, then we can play around with this idea of, okay, well let's see what happens when I physically add or subtract. And I suppose that depends on the trig, which trig ratio I'm using, whether I'd add or subtract, and make the difference too. So with this one, if I looked at in plus 2, I'd have cot to the power of n plus cot to the power of n plus 2. If I make that one complete integral and factorise, then I get cot to the power of n, 1 plus cot squared. 1 plus cot squared now allows me to use a trig identity. 1 plus cot squared is cosec squared. I can do a substitution, or if you notice it straight away, which I've done here, add 1 to the power over the power. So I've got minus cot to the n plus 1x on n plus 1. And then all I've got to do is rearrange the formula. But by the way, when I rearrange the formula, I don't make in the subject, I make in plus 2 the subject. Because it'll be the bigger one. Remember, we're trying to reduce. Now, if in plus 2 equals that, then I just basically substitute in n minus 2 for n. If I substitute in n minus 2 for n, I get my formula for in. I say that idea works okay, playing with true identities, and we're not using integration by parts. Alright, now let's work out I6. So I6, using our formula, minus a fifth cot 5 I4, sub in for I4, we reduce to I2. Keep going. Reduced it to I0, that's usually a good spot to stop because power of 0 will always equal 1. So in this case it's just the integral of dx, which is x. Integration by parts, terrific idea. Algebraic manipulation can be fun. You may not have thought of this sort of idea, but once you have it in your toolbox of ideas, something you can try. So in is 1 plus x squared to the power of n. They haven't told us what the formula is going to be, so we've just basically got to work it out. But at least they've told us the connection. We're going to reduce it by a power of 1 each time. So we've got to reduce by 1. So in is 1 plus x squared to the power of n. Going to reduce it by 1. Okay, well, I'll let u equal 1 plus x squared to the power of n, because if I integrate that, it's going to add to the power, not subtract to the power. Differentiate that, 2nx, 1 plus x squared, n minus 1. To v is dx, v is x. Sub that in, uv minus the integral of v to u. And I look at my new integral. And this is where the algebraic manipulation comes in. Instead of x squared, I'm going to write it as 1 plus x squared minus 1. That allows me to break this into two integrals. One of those integrals will be 1 plus x squared times 1 plus x squared to the n minus 1. And the other integral is going to be minus 1 times 1 plus x squared to the n plus 1. Why do that? Well, the middle one becomes 1 plus x squared to the power of n, and the second one stays as n minus 1. They're now things I can turn into in and in minus 1. I can now come up with a formula. So there it is, minus 2n in. Want to make in the subject. Remember, we make the larger one the subject. So playing around with that, I've got 2n plus 1 in. Divide both sides by 2n plus 1, and we have this incredible formula to use. So this, you'll notice examples like that a lot where you see that 1 plus x squared, where it's just got an x squared. So that idea of algebraic manipulation can come in quite handy. Alright, strap yourself in, because now we're going to look at some HSC questions. Start off with a straightforward one. 1987, very long time ago now. So in, they've told us what the formula is going to be. A lot of the times in the HSC they will tell us the formula for that reason. At least if you can't show the formula, you can show that you know how to apply the formula. So we know where we're heading to. We're going to reduce by 2, and then we're going to go and find the power of 5. Now, cosine, I've got a different technique depending on whether the power is odd or even. So I can't use one of our familiar techniques. So for that reason, I'll do it by parts. I mean, we don't normally do a cos to the power by parts. So cos to the power of n, I'm going to rewrite it. Well, how am I going to split it into two functions? I've got so many choices. I could say cos n times 1. I could say cos n minus 1 times cos. I could say cos n minus 2 times cos squared. I suppose theoretically I could keep going and keep going. So what do I try? Well, I just try something, and if it doesn't work, I'll try something else. So you'll notice cleverly though, I didn't try cos to the n first, because I knew that wouldn't work. So alright, so I'm going to try splitting it up, cos n minus 1 times cos x. Let's see what happens. So u is cos n minus 1. Differentiate that, minus n and minus 1, cos n minus 2, etc., etc. to v cos x. So v becomes sin x. Okay, sub it in. So uv, well, let's have a look at this definite integral. If I sub pi on 2 in, the cosine of pi on 2 is 0. So that'll be 0. Sub 0 in, the sine of 0 is 0. So, okay, that definite part that we've worked out is going to be 0. Now let's have a look at our integral. We have n minus 1 times cos to the n minus 2, but it's times sine squared. Well, I want to end up with the power of n minus 2, so I'm going to change my sine squared now. My sine squared, I can change into 1 minus cos squared, and then split that integral up into two things. And now I've got it, because the first integral is in minus 2, the second one I can write as in. And so we can now create a formula. So I've got in is n minus 1 in minus 2 minus n minus 1 in. We want to make in the subject. So n lots of in, divide by n, we've got the formula that they wanted. Okay. Alternative way, remember I said if trig 1s differ by 2, we could try playing around with it. Because they told me what the formula was, I can play around with this. So in minus 2 minus in. Okay. I know that would be cos n minus 2 by just cos n. Cos n minus 2, 1 minus cos squared, becomes cos n minus 2 sine squared. U equals sine x. Du equals cos x. I still have to end up using parts, you'll notice. Now, I'm not saying this is a fantastic way of doing it, by the way. But we do, eventually, come up with the same answer. So often when we're playing with trig and we know trig identities vary by 2, we can use this idea of, oh, let's have a look at in plus or minus in minus 2 or the other way around and let's see what happens. Probably not the way I would have done it. But it does work. I mean, it shows you there's an alternative way you could play with that one. Okay, let's work out I5. I5 will be 4/5 I3. I3, 2/3 of I1. I'm going to stop there because if I was to take 2 away now, I'll end up with a negative number and that's no good for me. So we're going to do the integral of cos. Integrate cos, we get sine, and then we sub in and we've got our answer. That's if I started at 5, worked my way down. Of course, you could have started at I1 and worked your way up. I mean, that's your choice. That was an example of a reasonably straightforward HSC question. Now comes 2004, which probably wasn't as straightforward, but gosh, it was fun. Let's have a look at this little beauty. We've got in, so that's the integral of tan to the power of n. We've also got this other expression, jn, which is minus 1 to the power of n I 2n. And I suppose that's just making sure that we're playing with even numbers for this second one, because multiply 2 by n, you're always going to get an even number there. Possibly that's why. Let's see. The first one, show that in plus 2 is in fact 1 on n plus 1. Okay? So they're actually forcing us to use that technique there, because it is going to be a quicker way. And I guess they just didn't want people wasting time, because this question has got quite a few parts to it. So integral tan to the n, tan n plus 2, combine it into 1, we get 1 plus tan squared is sec squared. We can now do a substitution, u equals tan x, which is sec squared. And limits, we've got to change our limits, so x equals 0, u equals 0, pi on 4, u is 1. And a lovely little integral to do, just u to the power of n. Add 1 to the power, over the power, substitute in 1, substitute in 0, and sure enough we get our required answer, 1 on n plus 1. Okay. Deduce that jn minus 1 is negative 1 on n to the power of, not to the power of, all over 2n minus 1. Well, they gave us a connection between jn and I. So basically I'm just applying that formula. Now, we also now just came up with a formula for in. So let's see what we can do here. Just going to rewrite that. So we have a common factor now, you'll notice, of minus 1 to the power of n. So all I've done there is go minus times minus. Okay. Pull out that common factor of minus 1 to the n, and inside the parentheses I have I2n plus I2n minus 2. So I've got I, and the difference between the subscripts is 2. We just created a formula for I, and the difference between the two subscripts were 2. So the answer was, when we added those two things together, was 1 over n plus 1. Okay, so this will be 1 over, but it won't be 1 over n plus 1. It'll be 1 over 2n minus 2 plus 1. And that's how we get there. So basically we're saying let n, in the first bit that we did, n is going to be 2n minus 2. And we end up with our expression. Okay, so when you initially see that question, it looks terrible. But actually, it comes out quite nicely. That last bit was good. Look at this one. Now we're going to show that jm, let's throw another pronumeral in there, is pi on 4, the sum of n equals 1 to m of that expression that we just worked out there. Okay. Well, we know that. Right? Because in part B, we just came up with an expression for, jm minus jm. So move it to the other side, and it becomes plus. But jm minus 1, I can apply the formula again. That's where this sum's going to come into it. So I'm going to apply it again, and apply it again, and apply it again, and apply it again. And the last time I would apply it would be when I get to J0. Okay, well let's have a look at what we've got here and start comparing. All this part, the minus 1 to the m plus the next one, dot, 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 actually is that sum if you look at it closely. Because the very first term is when I've got minus 1 to the power of 1 over 1. So that would be when n is equal to 1. The very first term works out when I just simply substitute in m for n. So I actually have that series there that they want. What we now need to do is work out what J0 is, and we're really hoping it turns out to be pi on 4. So pi on 4, well, it is, because it's just the integral of dx, and sub in pi on 4, sub in 0, and we get pi on 4. Alright. What a great question, eh? But it keeps going. Okay, now we're going to use the substitution u equals tan x to show this particular integral, in equals 0 to 1. Okay, in, remember, was the integral from 0 to pi on 4 of tan to the power of n x, but they've told us what they want us to do. They make life easier. So imagine you got part B and part C, which looked terrible. And I think it was question 8 in the HSC that year. So you've already done a lot of work, you're getting a bit tired, and so you're thinking B and C, and you're just going, oh God. D actually, if you look at it, is very, very easy. So a lot of people might have just blown it away because they're now in the mind of, oh my God, this question, I just can't, But you've got to dig deep, and sometimes there's gift marks in there, and this would be one of them. Because they've even told us, use u equals tan x. I'm going to play around with that a little bit tricky, but to make life really easy for myself. Instead of saying u equals tan x, I'm going to say x equals the inverse tan of u. Because if x equals the inverse tan of u, look what dx is. du on 1 plus u squared. And I can now sub in. I'll change my limits, of course. So tan to the power of n becomes u to the power of n. I'll just substrate in for dx. That's du on 1 plus u squared. And there's my answer. I've got it straight away. So I guess my little trick there was, instead of working out what du was and trying to manipulate it, is I made x a subject and said, no, I'll just substitute straight in for dx. Okay, so that was part D. But there was more. Okay. Now, we're going to deduce that in is always in between 0 and 1 on n plus 1, and then we should be able to conclude that as jn approaches 0, n will approach infinity. Yes, I'm sure you're looking at it too and thinking, well, that's obvious. Right. Let's see. In, we have now shown, is this expression, the integral of 0 to 1. That is always going to be greater than or equal to 0. I mean, everything there, because remember we're going from 0 to 1, so we're always substituting in positive numbers. Everything there is going to be positive. So, okay, so there's no question in is bigger than or equal to 0. The other end we've got to prove, of course. Okay. Now, remember this. We know that in plus 2 was equal to 1 on n plus 1. Was that way back in part A we did that? Or? So way back there we came up with that expression. So if that is true, just rearranging it, in is always equal to 1 on n plus 1 minus in plus 2. But remember we just said in is always positive? That means in plus 2 is always positive. Well, if in plus 2 is always positive, I'm never going to get more than 1 on n plus 1. So in must always be less than or equal to 1 on n plus 1, because we've just said that in plus 2 is always going to be positive. Now I've got in trapped in between 0 and 1 on n plus 1. Well, we know the limit as n approaches infinity of 1 on n plus 1 is 0. So as n approaches infinity, In is going to be in between 0 and 0. Well, that must be its limit then. So the limit must be In, but that's as n. They wanted to know what happens with j. Well, remember Jn was minus 1 to the n of I2n. Well, if I is approaching 0, then negative 1 times that must be approaching 0 as well. So my Jn, or m, or I might have put the wrong limit, but anyway, is going to approach 0.